Hello, my name is Juan Contardo, and my presentation is entitled Mapping the Distribution, Threats, and Protection Coverage of a Chilean Endemic Amphibian Considered a Living Fossil. I conducted this research with the Dr. Antonieta Labra. Today I'm going to talk about species distribution models that have become an undisputed and powerful tool to do wildlife research and conduct also conservation biology. They are also very useful to calculate the distribution of rare and very threatened species like the amphibians that are considered one of the most threatened taxa worldwide. For this study, we worked with Chilean endemic amphibian that is the helmeted water toad, or Calyptocephalela galli, that is considered a living fossil because it has survived with few changes since the Upper Cretaceous. And this is a species from family that is considered phylogenetically particular and that is also considered a paleoendemic clade. And therefore, it has a high evolutionary distinctiveness value. This species is currently undergoing population declines and is considered both by the IUCN and the Chilean environmental law as vulnerable. Well, within our main goals, we have calculate the suitable area for the Chilean helmeted water toad, evaluate the effectiveness of protected areas regarding the geographic potential distribution of this species, and carry out a geospatial risk analysis. I'm now going to talk about the methodology. We use occurrence data of this species that was collected from different sources, being the main one, the Global Biodiversity Information Facility, but we also collected data from iNaturalist, a paper published by Mora et al. In 2021, from social media citizen science forums, and also some dear colleagues shared their presence points with us, and we finally gathered a total of 176 presence records that you can see in the map on your right as green dots. For this study, we used environmental data, and there were two types of predictors, the bioclimatic and the topographic ones. For within the bioclimatic predictors, we use 19 bioclimatic variables from the WorldClim database. And within the topographic predictors, we use the altitude, land cover, distance from water bodies, slope, and the topographic wetness index. However, before conducting our SDMs, we did two previous steps in order to assess, to filter our valuables and assess some important topics. So the first step was to do a multicollinearity assessment where we assess the correlation among the predictors, and we estimated that a high correlation between pairs of variables was more than or equal to an absolute value of 0.7. And if we had a highly correlated predictors, we kept the one with the higher ecological importance and accuracy, and also the one that had the most relevant biological interpretation. After that, we did a variation inflation factor to ensure that there was no multicollinearity at all in our predictors data, and we make sure that this value was less than 5. After we filtered our predictor data, we got only 6 variables that were further used in our SDMs. There were mean diurnal temperature range, isothermality, altitude, distance from water bodies, land cover, and slope. The second step that we did before running our SDMs was assessing the spatial autocorrelation that we did using the other spatial package from our program. We used Moran's agent vector map analysis, and we conducted a mantle correlogram using 4 distance classes that you can see in this slide. And what we wanted to know is in which distance class there was no more correlation, spatial correlation. And after picking the distance class where there was no further spatial correlation, we do a data thinning of our presence points using the SP-thin package from our program. And finally, we did our modeling using the maximum entropy algorithm that is also known as MaxEnt. We used the SDM package from our program. We did 10,000 iterations of our model using 1,000 background points. And we also used a random partitioning process where we partition our occurrence data into 70% for training and 30% for testing our models. And we built a final assembled model where we only used models with a high performance. And for that, we used the following criteria: an area under the curve that was more than or equal to 0.85, and also true scale statistics that was more than or equal to 0.7. After obtaining our final sample model, we use it to build a binarized map of suitable and unsuitable areas. For that, we use a threshold based on the sensitivity, specificity, sum maximization approach. To measure the effectiveness of protected areas, we use this previously mentioned vectorized binary map, and we vectorized it using GIS, and then we intersected it with the Chilean protected areas layer, and finally we calculated the area of this intersection. For the geospatial risk analysis, we used the land use layer from the Chilean geospatial data infrastructure. However, there is almost no information about the risk that the different land uses categories pose upon the studied species. So we had to conduct a survey with 25 Chilean amphibian experts, where we asked them to put a numerical value to the different land use categories, being 0, the lowest risk for the species survival, and being 10, the highest risk for the species survival. After obtaining these numerical values, we averaged them and we recategorized them into 5 different risk categories. Very low risk from that have a value ranging from 0 to 2, low risk from 2.1 to 4, moderate risk from 4.1 to 6, high risk from 6.1 to 8, and very high risk 8.1 to 10. And we then intersected the vectorized binary map with this recategorized land use layer. I'm now going to talk about the results. The Moran agent vector maps analysis showed that there was a strong spatial autocorrelation, and the mantle correlogram yielded that the distance class where there was no further correlation was the one ranging from 8.1 to 16 kilometers onwards. So we used the upper value of this range of 16 kilometers to be conservative and to ensure that there was no spatial autocorrelation at all. So we use this distance for do the thinning of our occurrence data, and our occurrence points decreased from 176 to 77, and we finally obtained 194 models with optimal performance that were further used in our ensembled final model. In this picture, you can see on your left the final assembled model with a suitability that ranged from 0 to 0.95. And on your right, you can see the binary map that was then vectorized to calculate the total suitable area that was 50,118 kilometers square, using a threshold of 0.53. Regarding the relative importance of the environmental predictors, the three most important ones were altitude, Vauquelin 2 or mean diurnal temperature range, and slope. Here we have the response curves where we can see the behavior of the probability of occurrence regarding the five numerical environmental predictors. And I'm going to talk about the most important ones. You can see that the altitude had a negative correlation with the probability of occurrence. Then you can see that the probability of occurrence only have its highest value at low slope values, and the mean temperature range, diurnal range, was positively correlated with the probability of occurrence as we expected. So regarding the effectiveness of protected areas, we could see that there was little coverage of the suitable areas for our study species, only encompassing 3.55%. And the type of protected areas that had the best coverage was the biosphere reserve that covered 2.17% of the suitable areas of the helmeted toad. Regarding the geospatial risk analysis, the land use categories were classified depending on the risk they pose to the study species, and the urban and industrial areas were classified as extreme risk. Forestry land area without vegetation, agricultural land were classified as high risk. Meadow and scrubland, as well as mixed forest, were classified as moderate risk, and native forest, water body, and wetland were classified as low risk. There were no categories classified as very low risk. So then we can see that 60.61% of the suitable areas actually fell into extreme and high risk categories. So that is a very bad prognosis for our study species. In this figure, you can see in the letter A, the IUCN distribution map for the study species that is actually very similar to our results. And the lines are the limits of the distribution that are described by the literature that are 29 and 41 degrees south. And in the letter B map, we can see that our results extends the southern distribution of this species. So we strongly suggest to conduct a new surveys in this area that can be guided by the maps that we obtained. In this binary map, we can see that the northernmost suitable areas are very disconnected and patchy, and if there's any viable populations here, they must be subjected to a high extinction rate. So we strongly suggest to conduct conservation management measures as quick as possible, and new surveys and monitoring to quickly assess these populations. Regarding the geospatial risk analysis, there's a lot of area that has high risk. So we suggest that the Chilean governments should create new protected areas or at least promote the creation of private protected areas. And in the zones where they cannot create new protected areas, they can actually promote a shift in the human activities from activities that are a high or very high risk, like urban or mining activities, to activities that pose low risk, like ecotourism. We actually identified 3 river basins that are subjected to a high risk, where ONGs and environmental agencies from Chile should take conservation action. And these are from north to south: the Marga Marga River Basin, the Maules River Basin, and the Biobío Rivers Basin. We also suggest that conservation actions should be taken in the outskirts of Santiago and Concepcion, that are the biggest and most populated cities in Chile, where viable populations of the helmeted water toad still exists. This is the literature I cited in this presentation, and I don't know if there is going to be a Q&A section, but if you have any further questions, you can contact me to my email. Thank you very much.